So by simplifying the remote edge radar, we can reduce the compute requirements. We can use a cheaper and less power-hungry MCU there. It enables much more advanced algorithms and use cases. So not only can you deal with data from each radar individually and apply high-resolution direction of arrival techniques, for example, but you can also perform data fusion at the radar bridge level. Okay, hello everybody. I'm Gary Kerr. I'm from the Applications Engineering team in NXP, Radar Systems Group. I'm here to talk to you about a new system architecture concept. Distributed radar, physically distributed radar is a good way to understand it, but it also involves implementation of the trends of centralization and zonalization. It's actually a good follow-on from the Oxford RF presentation here. Okay, on the diagram, this is the traditional domain-based architecture. I think everyone here is familiar with this. Radar bridge is ADAS radar realization of software-defined vehicle trends. One of the proposals, or one of the options here, is to place a radar bridge processing ECU in the zone where the radar sensors on the edge of the vehicle are much simplified in comparison to the smart radars that we have established already. I'll talk in more detail about what exactly that means in terms of simplification and separation of responsibilities. There's also the option to use consolidated compute, so integration of radar bridge function into the vehicle computer or the ADAS SoC. So with traditional radar integration in the vehicle, we have fully comprehensive smart radar sensors on the edge. These are typically positioned on the four corners of the vehicle, and then a front-facing long-range radar in a sophisticated modern premium vehicle, you can imagine. Here, each of the radars has an MCU or a microprocessor inside with some sophisticated DSP capabilities, and also the RF there. So these edge sensors can be one-chip radar devices. NXP has several products in that style, or they can be separated MMIC and MCU combinations. But the important point is these ECUs are performing the full radar transceive and processing cycles at the edge, and they're going to provide tracked objects or target lists to the ADAS ECU for the decision making. So the vehicle network can accommodate this fully refined data in a CAN bus or a 100 megabits per second Ethernet. Distributed radar architecture is simplifying the sensors at the edge of the vehicle. We're still going to have very high performance and sophisticated RF, of course. This is the sensor head component, but we can simplify the MCU here. I'll explain why that's possible. The main point is that the bulk of the radar processing flow is going to be shifted into the radar bridge. So we can concentrate our compute resources, memory, also the power consumption can be optimized to reduce it at the edge and throw more resources at the problem in a central consolidated radar bridge. So one idea that we have proposed and implemented is to cut the radar signal processing chain after the first stage, the range FFT, 1D FFT. The data rates here for a 4x4 channel radar, as typical you would see in a one-chip radar device, you can accommodate within a 1 gigabit per second Ethernet link. So there is an added cost involved in upgrading that vehicle network to accommodate the higher data rates required, but there are optimizations possible at the edge for that balance. Now, a bit more detail on the system advantages. So by simplifying the remote edge radar, we can reduce the compute requirements. We can use a cheaper and less power-hungry MCU there. It doesn't need memory to buffer the full radar data cube. It only needs to buffer the ADC samples and FFT data for a single chip. Then we can transfer this over the network, 1 gigabit per second Ethernet or beyond that. Also SerDes options too. And we can complete the radar signal processing chain in the radar bridge. So we can reduce the compute, we can reduce the memory. By connection to a radar bridge, we can also start to eliminate components from the BOM. So we can have the remote radar be completely flashless and be booted over the Ethernet network. Of course, if you reduce the complexity on the edge, it also consumes less power. Now, we still need DSP and memory to complete the radar signal processing chain, but we have an opportunity in the radar bridge to elevate that, to concentrate the resources there. We can use much more powerful SoCs with expandable memory, DDR DRAM, multiple DSPs, multi-core MCUs and MPUs here. And we can share those resources amongst the data that's aggregated from multiple remote edge sensors. That's the point. So what does this bring you? It enables much more advanced algorithms and use cases. So not only can you deal with data from each radar individually and apply high-resolution direction of arrival techniques, for example, but you can also perform data fusion at the radar bridge level. It also opens up some of the techniques associated with software-defined vehicle, like over-the-air updates, delivered from the radar bridge to the edge sensors. And ultimately, the expectation is that you get better sensor performance by doing this. You can employ more memory and more advanced algorithms to improve the radar resolution and the number of targets that you can detect. Okay, so the processing split and the flexibility that radar bridge zonal or central processing gives you. So on the edge, as I mentioned, you still have full RF capabilities. You do your radar chirp sequence. We were typically working with FMCW, fast chirp radars, and we perform the range FFT. This is then where the partition happens, and we will transfer that data to the radar bridge, which can then complete the standard radar signal processing chain to the FFT detection algorithms and DOA. But it gives you huge flexibility and compute power to deploy more advanced techniques. So advanced algorithms like subspace-based DOA, music, esprit, you have the DSP, you have the memory now to do this. You can also look into interference mitigation, multi-frame techniques, and even more advanced approaches like Bayesian learning and lasso, Capon beamforming, all of these things which are high performance but compute intensive. At the edge, they're difficult to implement and still achieve a reasonable radar frame cycle time. With centralized processing in the radar bridge, you have better DSP and more memory. You can also envisage some AI ML implementation inside the radar bridge, usage of neural networks to perform DOA estimation, also inference and classification of the radar point cloud. So the radar bridge is still a companion to the main ADAS ECU, We can see a number of our OEM and Tier 1 customers. They have different ideas about what the output of the radar bridge should be. Many of them want the point cloud, as many points as possible, so they can feed it into an end-to-end neural network, which will, in their expectation, clean up the data and start to classify what the radar point cloud actually means in real terms. But other users are still interested in taking tracked object lists. So there's options for what strategy you take there in the radar bridge. Okay, here's a small example of the distributed radar in action. So NXP is a semiconductor supplier. We're not an OEM. We're not a Tier 1. Might be considered Tier Mobile now with our system solution step up. But we do still like to test our products. So we build evaluation systems. We use them in-house. We also deliver them to customers and partners. And this is an example of some real driving test experience that I personally had with a partner of ours. This actually just uses 4 corner radars, which are providing the 1D FFT, and then a standard signal processing flow that you've seen in the previous slide that results in a point cloud, and we use it for a 360-degree radar surround detection. And we took it on the roads and performed remarkably well. I'll point out that you can see quite clearly road boundaries. You can see other vehicles are represented there. And this is the data in its most unrefined form. And the edge sensors are actually 4 transmit, 4 receive, 1-chip radar modules. So they intrinsically don't have so many physical channels. We're using MIMO techniques to improve that. But the results are pretty good, and they are compatible to front-facing, multi-channel, massive MIMO imaging radar tests that we've also conducted. Okay, the core part of that is a development platform that I've been involved in. It's the NXP Purple Box. Here we're actually reusing one of our established imaging radar processors, S32R45, but we've taken advantage of its networking capabilities to build this platform. R45 is already in production. It's used in front-facing imaging radar applications, but it's directly connected to the radar front end, MMIC, via very short-range LVDS-based communications like MIPI CSI. So we've taken R45 and we're not using the MIPI CSI in this implementation. Instead, the sensors are providing the data via Ethernet. One of the key benefits here is we also have PCI Express support. So there's expansion capability. Many of our partners have added on NVMe SSDs. Really helps them to do data recording when they're performing field trials. But we also have partnerships with multiple ML AI companies who are promoting their products for neural network implementation at the edge. Many of them have PCI Express M2 modules, and we have software enablement support for those. I talked about this. So the NXP Purple Box actually uses all NXP Automotive solutions where possible, so it also has our in-vehicle networking products in it and power management ICs too. It's a reference design. Okay, this is my final slide, so I'll be quick. It's the block diagram, so I won't dwell too much on it. This is available on the Purple Box product page on nxp.com. But you can see here there's high connectivity. There's 5 1 gigabit base T1 Ethernet interfaces. So you can connect up to 5 corner radars or 4 corner radars in 1 front-facing imaging radar. And as I mentioned, it has PCI Express support too for expansion and data recording use cases. Yep, that's a quick summary of what sometimes is presented over 4 or 5 hours in 10 minutes. So I hope you got something from it, and if you have any questions, please let me know.